the recording, make sure we're all good.
I'll be honest, Rishi, I'm doing great. How are you doing?
That's good. Actually, yeah, yeah. I went home this weekend to my parents' house, and on the drive home, I was like, you know what? Life is good, man. Life is good. It was a good last week. We did some math. I played a little bit of frisbee. What
Okay.
more could a guy want? Truly, good
Those are the
stuff. Good
only
stuff.
two things I want.
Yeah, I haven't seen you
Yeah.
throw a frisbee
Oh,
before.
well, that's why I want it so bad because I just
Mm.
don't do it. I don't have a frisbee.
Yeah, yeah, yeah. No, no, that's fair. That's fair. I mean, what are you gonna do about it? I guess you could start playing frisbee, actually.
That is actually an actionable thing I could do
Yeah. Well, if you want, let me know. You can hang out, come play some
for
frisbee
sure.
with me.
For sure.
How's everyone
Um,
else? What are you guys up to? Good stuff. Good vibes. Good vibes. Good vibes. Cool. Nothing much. Yeah, yeah. I mean, it's summer, right? And it's a
oh,
Monday, so thank you guys for showing up.
congratulations, Angelica.
No, that's sick. That's sick. A
Oh my
birthday.
goodness.
Wow.
Happy birthday. Congratulations. You can join the military now.
That's true. That's true. You can go to the juror. You can become a juror now if you're an adult. Yeah. Which I have to do in a few weeks actually.
Dang.
But yeah, that's awesome. Happy birthday. Thank you for those of you who were here last Friday. We had a pretty good not deep dive, but maybe like a normal depth of dive into a day in the life of a college student. And it was good fun. I think that was pretty useful for those of you who are there. Again, if you have any questions about college, Nick and I have been through the ringer. So stick around in office hours, which will be directly after this in the Discord. So join my office hours if you have any questions. But yeah, we're gonna start off with a breakout room. Get you guys going, get you guys talking. Today, I want you guys to, similar to what we did last week for one of our breakout rooms, um, we're gonna put you in just two different rooms and share with each other. If you haven't introduced yourself, introduce yourself, whatever, your major, your name. And then talk about one thing that you're apprehensive for, nervous for, maybe a question, a doubt you have going into college, going into this fall semester, and then one thing you're really looking forward to. College is really exciting. Like, what's going to be, uh, what's the thing that excites you the most? Like something you haven't done before in college. So without further ado, we're going to break you guys into, those two rooms. Um, feel free to unmute, speak. If you're not able, use the chat. But I want participation from everyone if possible. All right, you got one and two rooms. All right. Go for it. See you guys in like 10 minutes.
Heck yeah, I'm
My
trying to
God,
join
my
on my iPad.
voice.
Hmm?
Okay, yeah, yeah, yeah. My voice was just gone, dude. I don't know. As soon as I started talking, wow. Yeah, I'm gonna pause the recording here.
Okay.
Um, resume that. Geometry is, I would say, the weakest topic for most people on the MPE. It comes up a decent amount, and it's nothing super complicated, but I think maybe for some people it's like they've forgotten some of these concepts. Other people that they might not have ever learned them. Maybe they haven't fully synthesized it, right? Like you learned how to find the perimeter of an object, but you just don't have like the practice with it yet, something like that. And so I would definitely say today, good session to attend because geometry is going to be the one that you might want to focus on more. So I highly, highly recommend you do the problems at the end of this worksheet. I was looking at them earlier today. They're all really solid problems. They're pretty good examples of what might come up on the MPE exam. So just as a reminder, at the end of every worksheet, there is in fact a problem set, geometry problem set. The first problem's review, so that's from last week, but the rest of these problems are all really good ones to take a look at. But we are going to start all the way at the top and see how far we get. So the first module of geometry just has to do with perimeter, area, and volume. So that's just kind of a reminder. Perimeter is the length of the outside of an object, um, which which is usually, fairly easy to calculate. You just kind of add up whatever the outside of an object, the lengths of each of those sides are. However, I will say for perimeter, what comes up a lot is, adding different perimeters together. For example, if you were to have an object that looks like this, let's say this length is 6, this length is 10, this length is 4, this length is 20. You might be like, well, I don't know exactly how to find the length of that object because, it's kind of a weird shape. I don't know what's going on. However, you can do a little bit of math to be like, okay, well, this 10 is the same as this 10 over here. And that 6 will probably be the same as this 6 over here. And then, well, if this is 20 and this is 4, then this plus this must equal, let's see, that would be 16, which means that this would be 8 and this would be 8. And then now you can add up all those numbers together, right? You would add 20 plus 10 times 2, because there's two 10s, plus 8 times 2, plus 6 times 2, plus 4, which would get you some number. And that would be your perimeter. So perimeter, just make sure that you use it as a tool if it ever comes up where you have a weird shaped object. Moving on, we have area. Area is the space inside of the object. And so here we have just a few different examples, equations that are going to be pretty common. So it kind of has a cheat sheet at the bottom here, but we have triangle is going to be 1/2 base times height. So if we have any triangle, this would be the base, this would be the height. So let's say the base was 8, the height was 10, then the area would be 1/2 8 times 10, which is 40, I do believe. Same thing for a rectangle / parallelogram. We have the length L and the height H square. We have length and length again because the height of a square is the same as its length. For a circle, we're going to have the radius, which is 1/2 of the diameter, squared times pi. So if the radius was 4, then the area of the circle would be pi times 4 squared, which would be 16 pi total. And just so we're clear, the units for perimeter is going to be whatever unit. So it's going to be like m, which is meters, or it could be like inches, or it could be feet, anything like that. For area, it's going to be units squared. So if they don't give you a unit, you would just write units squared. So for the circle, we would say like 16 pi units squared. So this it could also be meters squared, feet squared, inches squared, so on and so forth. It's important to keep those units in mind because sometimes you might have to convert between units. For example, let's just take a really simple example, a square. Let's make a square. I'll make this one a little bit nicer. So it's clear that it's a square. they might tell you, okay, what is the area in feet squared? That's the question. However, they might give you the side length in inches, right? They might say um, 12 inches by 12 inches. And so then you'd have to make sure you keep your units, right? You'd convert that. Maybe you want to multiply first. So you'd say 12 inches times 12 inches equals 144 inches squared. 144 inches squared. You would multiply that to see that we have 12 inches squared is equivalent to 1 foot squared. And so you'd see that the answer is 1 foot squared. Or you could just convert each of these, see that that's 1 foot, that's 1 foot. Therefore, the answer is 1 foot squared. So keep in mind your units. I'm just doing these examples to kind of illustrate what's going on. Personally, I'm a visual learner. And so when I see the equation, like, for example, this last one, the area of a trapezoid is base 1 plus base 2 times height divided by 2. I don't really know what that means. However, if I were you, I would just draw a little picture. Right? Trapezoid looks something like that. Okay, well, that was a pretty that was a pretty bad trapezoid. Let me use my little notability line snapping tools here to make it a little bit better. So we'll have the height, right? Or you could also label the height in there. And then you could say base 1 is that top side, and then base 2 is that bottom side. And now you have the equation for the area is going to be 1/2 base 1 plus base 2 times the height. Any questions with area or perimeter? Cool. I know this might be a little bit more basic for a lot of you, so that's why I'm going a little bit more quickly. But again, I do mean it from what our data shows. Geometry is definitely a harder topic for a lot of people, and it's not because geometry is anything crazy. It's just because you're not necessarily as refreshed with that topic. A lot of this you might have learned like many years ago, right? And so it makes sense. You might be a little bit rusty. Moving on, we're going to go into some equations for volume. So volume is going to have units cubed. So that could be meters cubed, could be inches cubed, whatever. It might be something, like millimeters cubed, right? You don't know. Any number of units, but make sure you have that cubed in there, right? Because volume is three-dimensional. It's the area within within that object. There it
Oh,
is.
you wrote inches squared.
Cool, cool, cool. Thank you. Always looking out for me. I appreciate that. Yes, it's always going to be cubed. That three, that three was not very artistic either. So there we go. Rectangular prism, length times width times height. So it doesn't really matter how you slice it. The length, the width, and the height. You don't have to orient your object in any way because no matter how you look at it, let's say this is width. Let's say you say the length is that that third dimension that goes into the page, and then the height is here. As long as you multiply them all together, you're going to get the same answer. So don't worry about which way the rectangle is facing. Cube, you know, same thing as a square. All of the sides are equivalent. So it's just going to be the cube of one of those sides. For a cone, we're going to go ahead and take the radius of the base. And then, yeah, 1/3 times pi times r squared. For a sphere, I'm gonna have, well, I can't really draw a sphere. Maybe that's a skill I'm lacking. Let's say, yeah, that doesn't help. Anyway, this is a sphere. You're just gonna have to take my word for it. From the center, the very center of that sphere to any outer edge is gonna be the same length, the radius. And so equation for the volume of a sphere is 4/3 pi r cubed. And
Uh,
for a
the
cylinder,
the cone should have a factor of h in it for height. It's r
yeah,
squared
yeah,
h.
okay, cool. Yeah, yeah, yeah. I was thinking about that. I was gonna come back to it, but did you look it up already?
Yeah.
Or did you just know it? Okay, cool. Um, yeah, note that typo. I was like, surely there's another thing, but I don't want to, misquote. But yeah, all the rest of these do look right. Cool. A little bit of a typo there. Nick, you are on top of it today, I have to say. In the back of my mind, I'm like, something suspicious there. But we got it. We got it. We've got our, helpful friend Nick always on the clock. For the cylinder, same thing with the radius. So it's the circle from either the top or the bottom. Uh, Radius is always going to be the same because it's a cylinder. The radius doesn't change. And then times the height. So radius squared times the height times pi. So you'll note there's kind of like a similarity between all of these. The cone, the sphere, and the cylinder, since they're all kind of like circular objects, or they at least have some semblance to a circle, they're always going to have a factor of pi. Um, you'll note that for cone, we were also able to find that mistake of a missing h, and the reason for that is because there is a height to it, right? And so anytime you're taking that MPE, you're like, I can't really remember what the sphere equation is, right? You might not have it. You know that you can at least get some work done if you remember, okay, what's in a sphere? Okay, what are the factors that go into it? It's radius, right? There's not really much else to a sphere. There's no height because the height of a sphere is related to its radius. For a cylinder, let's say you really cannot remember what the equation for a cylinder is. Um, all you're doing is you're taking the area of this circle, the top circle, which is pi r squared, and then you're multiplying it. You're kind of like slicing it, or adding a bunch of slices together times this entire height. So some of these equations, you might not exactly remember, oh yeah, there's a 4/3 in this equation, or there's a 1/3 in this equation. But you try to use like a reality check, right? Try to make sure that you have some idea of like what factors are going into these different uh, equations. So that's just one like not even a piece of advice, but just like try not to get bogged down by the exact equation. Just think about like what's going on. What attributes does each of these shapes have? Cool. Any questions so far? Again, I'm trying to go through these equations kind of quick. I mean, they're all relatively straightforward. Okay, no questions. Cool. So this is an important point. Area or volume of complex shapes. We don't know what the equation of a hexagon is. I mean, we do, but it's not something you might have off the top of your head. So a good habit to have, just like what we did with this problem at the very top with perimeter, is relating shapes to one another. If we're ever given a shape, a complex shape, it's a really good habit to be able to um, break it up into smaller pieces or take smaller pieces and build them up into something bigger. So the hexagon is a six-sided shape. If it's a perfect hexagon like this, which means like each of these sides are the same length, this little line that is I'm drawing in each of these sides indicates congruency. So that means they're the same. If you have a hexagon that each of the sides is the same, and they're giving us what almost looks like the radius. It's not because this is not a circle, but if they're giving us this side length, we can use the fact that each of these like kind of sections of the hexagon are the same, like so. Right. So if we know this is two, then we know this is two, then we can kind of break it up into a bunch of different pieces like so, right? So you could break it up into that piece, that piece, that piece, that piece, that piece, which comes out to six pieces. And so yes, we don't have the equation for polygon like this, a hexagon, but we can break it up. Does that kind of make sense? Make it a thumbs up in the reaction window if you're understanding what I'm saying about breaking things up. Cool, cool, cool. Right. Because this comes up a lot, right? They're usually on the MP. They're not going to ask you like, okay, what's the equation or what's the area of a triangle? However, they might ask you like, oh, what's the equation or what's the area of a hexagon? They're going to try to like challenge you and take it like one step further than like kind of like the base knowledge. Cool. Speaking of which, let's do an example, right? So you'll note that in this example, there's a lot of words and there's not just like one thing that they're asking you to do. They're not just asking you like find the area of a cube, right? For this one, they're going to be asking us about a baker that creates fantastic cupcakes. Now, maybe I'm just hungry, but that sounds pretty good. Let's see. They're making a huge order of 75 cupcakes in a large box that has 3 layers of cupcakes. So a cupcake has kind of an odd shape. So just to make it simple, what they've said is that we're going to put each cupcake into a cube of side length 3 inches. So first thing I'm going to do is just go ahead and draw what that means, right? A cube looks something like this. This is 2 inches by 2 inches by 2 inches. Then they're saying that we want to deliver these cupcakes to stores in batches of 75. 75. And that has 3 layers of cupcakes, which means 3 layers of box, essentially. And so now I'm going to kind of draw a picture, right? I'm a visual person, so I highly recommend that you do a little something like this. I don't really know what this box looks like quite yet, so I'm just going to draw a big old box. Oh, draw a big old box like so. They say each uh, each of these boxes, or this entire box, has 3 layers of cupcakes. So what I can do is kind of split up whatever our big box that holds 75 into 3 layers of cupcakes, because it says that piece of information right there. So with that piece of information, we already know one side of our box's dimensions, right? So if it's 3 cupcakes high, this is 2 inches, 2 inches, and 2 inches. We know that this is going to be 6 inches tall, that side of the box. We also know that we have 75 cupcakes total. So 75 divided by 3 means that we have 25 cupcakes per layer. Cakes per layer. So each of these layers is going to have 25 cupcakes. So, what else do we need to do to kind of find out what the dimensions of this box are? Because in order to find the volume and surface area of the box, we need to know what the box looks like, right? All the equations that we have, the ones that I just covered for volume and surface area, have to do with the dimensions of that box. And so what we're going to do to make it nice and easy is make a square, okay? We have 25 cupcakes per layer. The most effective way to hold something, well, I guess the most effective way to hold like any amount of things is a square, right? A square is a very efficient design. Um, this might even be a typo, but they kind of give us a hint. There's a square base. They say that for this first part, they're saying that there's um, a cube of side length 2 inches, and that cube has a square base. However, we know that's redundant because a cube already has a square base because it's cube. Okay, all of the sides are the same. It's entirely made up of squares. So I think they might have been saying that the base of the large box is a square, but in any case, I'll tell you right now, a square is the most efficient design. The reason for that is a little bit more complicated. There's a whole actually a calculus problem you could do about like optimizing shapes and finding out what the optimal design is. However, we're not taking calculus right now, so we're just gonna kind of say a square is the most efficient design. So all that to say, this is going to be 5 cupcakes by 5 cupcakes. So if there's 5 cupcakes here, it's going to be 5 times 2 inches. There's 5 here, it's going to be 5 times 2 inches, which means they're going to have 10 inches by 10 inches. So what is the volume of the box? Volume equals 6 inches times 10 inches times 10 inches, right? Because it's going to be uh, the height times the width times the depth, or whatever 3 dimensions you wanna call them. But it's the height times the width times the depth, which is going to equal 600 inches cubed. It's also asking us, what is the surface area? So the surface area, a little bit more complicated. The equation for that is a little bit longer. But essentially, it's just going to be all of the sides of this box added together. We know there's 6 sides to this box, right? The top and the bottom are the same. So this guy up here is the same as this guy down here, this bottom side. They're both going to be 10 by 10 inches. And then we also know that we have 4 sides. We have the 4 sides that are all like this shape, right? Which is that 6 inches tall and 10 inches wide. So what we're going to do to get our answer for surface area is break it up into a bunch of shapes. Like I kind of said at the beginning, it's a tool that works pretty well for a lot of geometry problems. So we have 2 of the top and the bottom, right? We have the top and we have the bottom. So it's going to be 2 times 10 inches times 10 inches plus 4 times each of those sides, right? We have 4 different sides to this box. So 4 times 6 inches times 10 inches. So it's going to be 200 plus, I believe that's 240. And so we should get 440 inches squared. Now I really want a cupcake, but that's okay. I'll wait till after the section to do that. Any questions with that problem? Cool. Okay, no questions today. No questions. Please feel free to speak up. If I'm ever doing a problem, I make a typo, or you have a question. There's no such thing, as a bad question or anything like that. We're all just trying to review, right? But if there truly are no questions, I'll keep going onwards. What was that, Nick? Is that a balloon? Are you making balloons appear
It's
on
a
the
lot
screen?
of balloons.
Oh my gosh.
This
How
new
you
Zoom
doing?
update's crazy.
There's a Zoom update, was there?
Yeah.
Okay, okay. Well, I'll have to check that out. Maybe when you're doing your half of the section, I'll like go in and start like dropping
Yes,
all
please
these
do.
different crazy. Yeah, okay, perfect. Okay.
Throw off my rhythm.
No, it really doesn't throw me off though. It's cool. It's like, oh, cool, like balloons. It makes me happy actually. Like something
Okay.
about balloons, so like therapeutic to the mind, because it was
Yeah.
associated with very happy things.
Yeah.
Of course. Okay. So geometry. When I personally think about geometry, someone says the word geometry to me, I think triangles. Triangles are, I would say, the most common thing we talk about in geometry, just because they're very, very useful, and also very peculiar. Triangles have a few different rules that we have to follow. So module 2 is just dealing with all about triangles. A little bit of vocab here. I'm going to grab my highlighter to kind of highlight these things. There are three types of triangles, and they all have to do with their general shape. Equilateral, it's kind of in the name. Equal means that all three sides are equal. Isosceles is where we have two sides of equal length. And then scalene, this one I kind of think lean, it's kind of lopsided, and that's how I remember that um, all of the sides are of different lengths. So this thing doesn't look very well pretty. It's kind of like uh, all three sides are different lengths. We don't there's no like special, you know, two sides are the same anything like that. Two angles are the same. It's kind of like a hodgepodge of different things. Then we have a separate but also a group of three. We have right, obtuse, and acute triangles. And these have to do with the angles of the three interior angles of the triangle. So a triangle, all of the angles inside of it add up to 180 degrees. Um, a right triangle is one where the angle is 90 for one of those three angles, 90 degrees. So it's a right triangle, very useful. You might use that in like construction, for example. It's very important that things are nice and right angled to each other, right? You look around your room, all you see are right angles. Obtuse means that one of the angles is really big. So this angle here is just larger than 90 degrees, which means these other two angles are going to be pretty small. They're going to be smaller than 90 degrees. Then we have an acute triangle, one where one angle is between 0 and 90 degrees. Or sorry, all well, I mean, since all of these are equal to 180, if one of them is between 0 and 90 degrees, all of them will be between 0 and 90 degrees. Or that's I said that backwards. All of them are within the range of 0 to 90 degrees because, let's say one of them is like 89 degrees, that leaves only 91 degrees for the other two angles. And so you kind of can figure that all of the angles are less than 90 degrees. So kind of not really a rule, but essentially, yeah, you have small angles for all of them. Um, One thing, food for thought, that I want to point out is comparing these two different lists. Okay, so we have right, obtuse, and acute. Then we have equilateral, isosceles, and scalene. So just for a second on your own, I kind of want you to think about how some of these could relate to each other, right? Like, can we have an isosceles triangle that's also a right triangle, or could we have an acute triangle that's also scalene? There are ways that we could have um, one from one list and one from the other list. We could also say that you know if we have a scalene triangle, is it possible for us to have a right triangle? Like, is that possible to have them both at the same time? We can ask ourselves these questions and kind of use one piece of information to help us with another piece of information, which is something that's going to come up in some of the practice problems on the website, on the MPE website. And so I won't like list out a bunch of different uh, statements you can make, but just think about it for a second. How could you use one piece of information from one list to relate to something on the other list? A little bit more vocab. Bear with me here. I'm almost done speaking. We're going to talk about congruent, complementary, and supplementary angles. Congruent angles, it just means they're the same angle. Complementary angles equal 190 degrees, and supplementary angles equal 180 degrees. So essentially, if you have like a right corner like this, then you know that whatever's in there, whatever angles are going on, must equal 180. And then if you have a line, like let's say you have a line like this, if you add up, like you have an angle, a bunch of angles like that, they must all equal 180 degrees, right? Because that one half of the line is going to be equal to 180. And then last but not least, we have vertical angles. If there are two crossed lines, the opposites are going to equal each other, right? So here we have 1 and 3 equal each other, and 4 and 2 equal each other. Not vertical angles, that's when we have two not lines, right? So this, note that that's not a line, right? It's just a line segment and another line segment that kind of look like they're straight, but they're not, right? You can clearly see that there's an angle there that is not 180 degrees. Same thing here, right? We have one straight line and then we have one bent line. So that does not count, does not help us. And then theorem, don't worry about like what number theorem it is. But if we have two parallel lines and you draw a line across it, then the same like matching angle where that one line, this line one corresponds or intersects, sorry, where one intersects J is going to be the same angle to where one intersects K, right? So 2 and 6 in this case, those two angles are going to be congruent angles as well. So most of these things are kind of, you can kind of tell, right? Like 2 and 6 kind of look similar, but note that you're actually following these rules because what they like to do is on tests, they'll make two things look similar, but you don't actually know if they're similar or not. So you have to know that you have to have two parallel lines and then one of them is crossing both of them. Um, you have to know what situations these actually apply to, because don't just trust your eye, right? If you look at it on a test and it doesn't actually say like, oh, these two lines are parallel, or uh, you know, this is a square, right? Maybe something looks like a square, don't assume it's a square. You have to know, okay, a square has four sides that are also the same length. Does that kind of make sense? Because that is I would say, a very important point is don't trust your eyes, trust the numbers on the page. Thumbs up if that kind of makes sense to you guys, because trust me, it'll come up on the MPE, right? They're going to try to trick you. Wow, Nick, you really understand that. You really understand that, don't you? All right, cool, cool, cool. Finish up with um module 2. Nick, do you wanna take over now? Is this a good kind of stopping point before we get into some more theorems?
Yeah, let me switch over to my screen.
Cool. Yeah, last thing I'll say is triangle inequality theorem. Um, the sum of two sides must be equal or must be greater than the third side, which makes sense, right? If you have two sides, third side must be shorter than those two. That's kind of common sense, but it is a theorem. And with that, I will stop sharing my screen. All right,
And I will start sharing mine.
all you, brother.
Okay. Cool. All right. Um, First of all, I want to say for the triangle inequality theorem, the reason that's a thing, and this is a thing in Math 18, which Rishi and I both tutored, so I've drawn this a bunch. But if you have a triangle, um, for if this is S3 and this is S1 plus S2, and these were equal, these would just be two parallel lines. And you couldn't make a triangle out of it. You need S3 to be just a little bit shorter. S1, S3. You need S3 to be just a little bit shorter than S1 plus S2, because if they were equal, then S1 plus S2 would have to like be like collinear on the same line to to equal S3, and then you wouldn't have a triangle. So that's why the triangle inequality is a thing. Yeah, just a little graphical thing I like to show. It's not super important though. Okay. Going on to whatever the equivalent of an international superstar in the math world is, Pythagorean theorem. This holds for every single triangle. Um, oh, sorry, every single right triangle. My bad. I'm not gonna mess up this early. Every right triangle you can apply this to, where if you have side lengths A, B, and C, it doesn't and where C is the hypotenuse of the right triangle and A and B are the two legs, you have the A squared plus B squared equals C squared relation. There's a bunch of nice graphical ways to show this, but I'm sure you've seen this a bunch, so I won't dwell on it too much. But this one comes up a lot, and it's a foundation for a lot of stuff you see later in math, vector calc and stuff included. That's like Calc 3 and onwards. So yeah, so let's talk about some specific right triangles. Some ones that you're gonna see very commonly. Perhaps the most common one you'll see is the 45-45-90 triangle, where you have the 90-degree angle making this a right triangle, and then the other two angles are equal. And note that because everything adds up to 180, and you have 90 plus 2 times some angle, that has to be 45, right? Just solving for that angle. And the main thing to note with these triangles is that these two side lengths here, corresponding to the two smaller angles, are going to be equal. And if we call those lengths x, then the hypotenuse, which is not going to be the same, so I give it an extra line, is going to be equal to x times the square root of 2. And we could actually solve for this using the Pythagorean theorem, where, for example, if we just call the hypotenuse h, we don't know what it is yet, and we solve for it, we can see that we can add the two side lengths like so, and then square root both sides to solve for h, where we're left with the square root of 2 times x equals h. Okay, and so if you ever see a triangle of this format, you know that you can just instantly calculate the hypotenuse. Oh. Yeah, that works too. I forgot that it's written right below this. Oops. Anyhow, I can check my work. Okay. Next most common is the 30-60-90 triangle. So obviously we have the 90-degree angle making it a right triangle. And then one angle is 30, one angle is 60. In this case, the side relation that we can memorize is the shortest side, which will be opposite the smallest angle. If we just label that as x, then the longer of the two legs, the one opposite the 60-degree angle, is just going to be the square root of 3 times that length x, and the hypotenuse is just going to be twice that short side length. And we should be able to see that if we were to put this through the Pythagorean theorem and calculate, we get x squared plus root 3x squared is just going to be 3x squared. Oh, oops, that's an equal. And then this is going to equal 4x squared, which is true. All right, and this is one that maybe you have it memorized, maybe you don't, but it's good to keep in your back pocket because these triangles do come up fairly frequently. As you can see here, this equilateral triangle And you could actually divide an equilateral triangle into two of these triangles and actually derive some of the equations for equilateral triangles from this 30, 60, 90 guy. Okay. And then if the Pythagorean theorem is John or Paul from the Beatles, then the trigonometric ratios are like, I don't know, George or another member of the Beatles, because these are just as important, and really really fascinating because sine and cosine tangent start off as um just ratios that relate to triangles. And then as you go on and you go on, they never stop showing up. And they develop all of these new applications. They pop up where you don't expect them. There's like I mean, if you're a fan of math as kind of like almost like a mystical art, uh, then these trig functions have a lot of mysticism behind them because they just show up out of nowhere and they never go away. They're super useful. Um, and they all come from a very simple concept where if you have a triangle, specifically a right triangle, um, and this is the hypotenuse H, and we'll call this leg A and leg B. I'm going to call this angle the Greek letter alpha, and this angle the Greek letter beta, as I think is typical in these kind of trig proofs. Um, the terminology is that the sine of alpha um, equals the side length A over the hypotenuse. As you can see here. Sine, cosine, tangent are all functions, similar to the polynomial functions we've studied already, that take angles as inputs and give out a value, specifically these guys give out a value between -1 and 1. And what that value is referring to is the ratio of this side length to the hypotenuse. It should always be less than or equal to 1, considering the hypotenuse should always be the longest side, right? So that there should never be any numerator that's greater than the denominator. But yeah, so the sine of any particular angle is the length of the opposite side over the hypotenuse. The cosine of any particular angle is the adjacent side to it. So angles here, this is the adjacent side, like so. And then finally, tangent of a particular angle is going to be the opposite side over the adjacent side. The way we like to remember this, I'm sure you have seen this in the past, SOHCAHTOA, standing for sine opposite hypotenuse, and then cosine adjacent hypotenuse, and then finally tangent is opposite adjacent. So SOHCAHTOA. Okay, cool. And yeah, like I said, these will never not be useful in your math journey. So the earlier you get familiar with them, the better. Okay, cool. So let's do a couple example problems using some of the angle relationships that Rishi just talked about. First of all, we'll start with 2.1 question 1. We want to find the value of this angle x. Feel free. Yeah, Ringo. I didn't say Ringo earlier because I don't know. It almost feels disrespectful to call call someone the Ringo. He's a great drummer and all that, but you don't want to be called the Ringo of the Beatles. Um, okay. Uh, who can type in chat? What is this value of x going to be based on some of the angle relationships we've seen? 28. I agree. 128. Um, yeah, and so this is called a corresponding angle, right? I could scroll up and see that. Or the yeah, vertical angle. I'm confusing my terminology. But if you have two lines that intersect, the lines that are opposite each other are going to be equal. So x equals 128. X equals 128. Okay. Question 2. We have a right triangle. One angle is 68 degrees. Then we have x. What can we expect x to be? Beautiful. Looking good. We use the fact that for a right triangle, 68 degrees plus x degrees must equal 90, right? The right triangle is 90. These are complementary. They must add up to 90. So x has to equal 22. Highlight that, highlight that. Okay. Here, we're trying to solve for x. We have this angle 5 times x and this angle 113. Now, I'm not going to ask you guys to give this angle. I don't think it's going to be a nice number. But we can use the fact that these are both angles that together add up to 180, right? We have a line. Total angle over a line should be 180. So 113 plus 5 times x degrees. It's going to give us that. Subtracting 113 is going to give us 67 degrees equals 5x. And then x is going to be whatever 67 over 5 is. 12 point or 13.4, I think. I'll double check that, but I think that's what it is. 13.4, yeah. Okay, cool. And then finally, we have a situation similar to the one we saw in part 1, where because these are vertical angles, they're opposite sides of two intersecting lines, they should be equal to each other. So here, 2x plus 1 equals 75. That means that 74 degrees equals 2 times x degrees, which gives us 37 equals x. Okay, cool. Everybody feel good about that? These angle relationships? Okay, cool. I think when you see cases like this, it's easy to recognize what you're supposed to do. I think the slightly harder thing to do is sort of with a complicated setup, identify where the vertical angles are, where the congruent angles are, what kind of assumptions you can make. And that just comes with practice. So I definitely recommend, 100% recommend giving these geometry practice problems a try after we're done with the geometry section. Okay. Uh, for 2.2, want to know what is the measure of angle C? Well, we know that we have angle 72 here. We also know that these two sides are equivalent, right? So what do we actually have here? It's kind of hard to see as drawn, but we have an isosceles triangle where we have two sides that are equal, like so. And what do we know about isosceles triangles? Well, if this top angle is one angle, then these two should be equal to each other, right? The opposite sides are equal to each other, so they should be equal angles. So we can go ahead and just call this X, and this is also X. So we know that X plus 72 degrees equals 180 degrees because that is the inside of a triangle. So 2x should give us 108 degrees, which means that x is going to give us 54 degrees. I guess angle C is 54 degrees. Okay. We recognize that the type of triangle, which tells us some facts that we can use about the angles' relationship to one another, that we can then use to create an equation that we can solve for x. So that's kind of the workflow with working with triangles. The first part of any geometry problem, usually, for me at least, is just looking at it and being like, what do we got here? Based on what I've been given, what kind of shape am I looking at? Because that's going to tell you a whole lot about which equations to use and what's going to be equal to what. Okay, cool. And Rishi, we have 13 minutes left, but we probably are not going to have an adequate amount of time to finish this. So I'll probably just finish this example and then we'll call it.
Yeah, sounds good. Sounds good.
Okay, cool. So we'll do this last example and then we'll save the rest of geometry for tomorrow, which is totally okay. We're still on pace. So let's do this last example. Note we have a right triangle, so that already tells us a lot. We can use trig functions. We can use, if it's a 30, 60, 90, which in this case it is, we already know some of the relations we can use. And so that's going to save us some time. The problem's asking find the missing sides in the triangle. Okay. Well, as I just said, it is a 30, 60, 90, which is very good for us because we know what the side relations are in a 30, 60, 90 triangle. We know that the short side, if we call the x, the long side is just the square root of 3 times that side, and the hypotenuse is 2 times that side. In this case, 4 is opposite the 30-degree angle. It's the short side. So, A, which is the length of the longer of the two legs, is just 4 times root 3, and we'll just call that units. We're not given any units, but we have to indicate that we're referring to length, so we write just units. It's 4 root 3 units long. C, which is the hypotenuse, is just 2 times 4, or 8 units. Okay. we could trying to think of other ways to solve the problem. Oh, we could use trig functions using the fact that sine of 30 is going to equal opposite, which is 4, over the hypotenuse, which is c. And then rearranging, we get that c is going to equal 4 over the sine of 30 degrees. Who remembers what sine of 30 is off top? It's okay if you don't, but I don't remember if it was if unit circle was as drilled into everyone's head as it was into mine. I had a pretty extreme algebra 2 trig teacher. Uh the ratio, and you might just be able to figure this from what it should work out to be. The ratio is actually 1/2. Sine of 30 is 1/2. Um, so 4 for 1/2 is going to give us 8 units. And then we know that A equals, well, tangent of 30 degrees equals opposite, which is 4, over adjacent, which is A. So A equals 4 over tangent of 30, which tangent of 30, not one that you probably had to memorize, but tangent of 30, I believe, is root 3 over 3. Which is equivalent to 4 over 1 over root 3, which gives us 4 root 3 units. So there's two ways we could have solved this problem using trig functions and sort of working backwards to find the side length, or just using the knowledge that it's a 30, 60, 90. We know what the relations between the sides should be. Okay, cool. Does anyone have any questions on what we did in any of these examples? Okay. All right. If you're still typing, that's fine. If there's no questions, uh, then we will be calling it. Tomorrow we are going to go over, for me, what I remember the most as being a pain in geometry, which is these congruence theorems, how to tell if two triangles are congruent to one another based on sides and angles and stuff. Um, that will, it's likely that that will be on the MP. It's like almost guaranteed, I would imagine. Um, so definitely be sure to be here tomorrow. We'll go in depth on these and it should be really helpful. Um, cool. Rishi?
Yeah, no, definitely be here tomorrow. I would definitely say most of the topics this week, until like Thursday, are going to be like a little bit more challenging than last week. And that's good because that means you'll be able to nail them on the MPE. Friday, just as a kind of looking ahead, will probably be like a little bit shorter of a day. So don't really stress about that day. But only 3 more days essentially is what I'm trying to say. Tuesday, Wednesday, Thursday, be here, be square or triangular, whatever your choice. And trust me, being here for those 3 days will pay off so much for your career in college. Because if you get placed into a better class because of that, you'll be saving yourself like months and months of work. So truly, um, truly try your best to be here for the rest of the week. Thanks you guys who are here. And yeah, we will see you guys tomorrow. Stick around in the Discord office hours if you have any questions.
All right. Thank you very much. Easy W. Easy W.